Hello, viewers. In today's session, we are going to discuss an important and conceptual problem from continuity and differentiability of functions. Right. So here we are going to discuss this problem in which we are given a function f of x, which is equal to the greatest integer of x plus 3, and we have to see the continuity and differentiability of this greatest integer function, that is greatest integer of x plus 3. At this point x is equal to 1 over 3. Right, so here we'll see the steps how we can prove the continuity or the discontinuity and the differentiability or the non-differentiability of functions using the given concepts. Right, so let us start. So let us first see the continuity of this function, and here to prove the continuity of a function at a given point, say x is equal to a, and if we are given a function say y is equal to f of x, what we do, we find out the right hand limit and the left hand limit and the value of the function at the given point. Here the point is x is equal to a, and if all these three quantities are finite and they exist and they are equal to each other, then we can say that the function or the given function is continuous at this point x is equal to a. Right, so in our case we are given this function and the point x is equal to 1 over 3 is a. Right, so let us first find the right hand limit, and then we'll find out the left hand limit, and then we'll find out the value of the function at a is equal to 1 over 3. So the notation for the right hand limit is given by limit x tends to, here we'll write a, and here we'll write a positive sign, and here we have f of x. So a is 1 over 3, so we have x tends to 1 over 3 positive, and here we have f of x. Right, so let us take x is equal to 1 over 3 plus h, where h is a very small quantity or it is infinitesimally very small. Right, so here we have x is equal to a is equal to 1 over 3. So when we calculate the right hand limit, we approach from the right of x is equal to 1 over 3, and we are in the neighborhood of x is equal to 1 over 3, that is the right neighborhood, and this point is 1 over 3 plus h. And when we calculate the left hand limit, then we approach from the left of x is equal to 1 over 3, and we reach at a point in the left neighborhood, that is x is equal to 1 over 3 minus h. Right, so we take x is equal to 1 over 3 plus h for calculating the right hand limit, and here when x tends to 1 over 3, then h tends to 0, and remember h is a positive quantity, and it lies between 0 and 1. Right, so now the right hand limit can be written in terms of h. So we have limit h tends to 0. For x tends to 1 over 3 positive, we have h tends to 0, and here we have f of x. X can be replaced by 1 over 3 plus h. So we have limit h tends to 0. F of 1 over 3 plus h can be obtained by replacing this x by 1 over 3 plus h. So we have greatest integer of 1 over 3 plus h plus 3. Right, so now we can simplify this expression. Then we have limit h tends to 0, and here we have 1 over 3 plus 3 is 10 over 3, and here we have h. So now let us see this term inside the greatest integer function symbol. So we have 10 over 3 plus h. Now when we divide this 10 by 3, we get approximately 3.3, and then we add h to 3.3. Now see, h is a very small quantity. So when we add h to 3.3, then this term, that is 3.3 plus h, is greater than 3, but it is less than 4, right? So in other words, we can say that this number, that is 3.3 plus h, is lying between 3 and 4. So the greatest integer of 3.3 plus h is equal to this number 3 by definition of greatest integer function, right? So we have limit h tends to 0, and here 10 over 3 plus h is 3.3 plus h, and this is equal to the greatest integer of 3.3 plus h is equal to 3. So we have simply 3, right? Because this 3 is independent of h. So limit h tends to 0, 3 is equal to 3. So the right hand limit of this function at this point x is equal to 1 over 3 is equal to 3. Now let us calculate the left hand limit. So now the notation for the left hand limit is given by limit. Here we have x tends to a negative. Here we put a negative sign, and here we have f of x. So this is limit, and x tends to 1 over 3 negative, and here we have f of x, right? So now to calculate the left hand limit, we take x is equal to 1 over 3 minus h. So when x tends to 1 over 3, h tends to 0. So now the left hand limit in terms of h is given by a limit h tends to 0, and here we have f of 1 over 3 minus h. So now we can write limit h tends to 0. F of 1 over 3 minus h can be obtained by replacing this x by 1 over 3 minus h. So we have 1 over 3 minus h plus 3, and now we have limit h tends to 0, and we have 1 over 3 plus 3 is 10 over 3 minus h, right? So again we have here this expression, that is 10 over 3 minus h. Now 10 over 3 is approximately 3.3, and here we have minus h. So h is again infinitesimally very small. So when we subtract h from 3.3, then this number is again greater than 3, but it is less than 4, right? So 3.3 minus h, or 10 over 3 minus h, it lies between 3 and 4. So by the definition of greatest integer function, the value of greatest integer of 3.3 minus h is equal to this number 3, right? So now here we have limit h tends to 0, and here we have greatest integer of 3.3 minus h, and this is limit h tends to 0, and greatest integer of 3.3 minus h is 3. So limit h tends to 0, 3 is equal to 3, because again here this term is independent of h. So we see that the left hand limit of this function when x approaches to 1 over 3 is equal to 3, right? Now let us calculate f of a. So f of a is given by f of 1 over 3. So we have f of 1 over 3 can be obtained by replacing x by 1 over 3. So we have 1 over 3 here and plus 3. So this is greatest integer of 10 over 3, and this is greatest integer of 3.3, right? So approximately 10 over 3 is 3.3. So again, by the definition of greatest integer function, 3.3, it lies between 3 and 4, right? So the greatest integer of 3.3 is equal to 3. So f of 1 over 3 is equal to 3. So we can see that the right hand limit, it exists and it is finite and it is equal to 3. The left hand limit, it exists and it is finite and it is equal to 3. And the value of the function at x is equal to 1 over 3, it exists and finite. So f of 1 over 3 is equal to 3. So these three quantities are equal to each other. So we can see that the right hand limit is equal to left hand limit is equal to f of 1 over 3, and this is equal to 3, right? So we can now claim that this function is continuous at x is equal to 1 over 3, right? So now let us see the differentiability of this function at x is equal to 1 over 3. So now to test the differentiability of this function at this point, we find out the right hand derivative and we find out the left hand derivative, right? And if the right hand derivative, it exists and it is finite, and similarly the left hand limit, it exists and finite, and both are equal to each other, then we can see or we can claim that this function is differentiable at this point, that is x is equal to a, right? So the definition of right hand derivative is given by this limit, that is limit x h tends to 0, and here we have f of a plus h minus f of a divided by h. So this limit gives us the right hand derivative at this point x is equal to a. So the notation, this notation can also be used f prime, and here we write a positive sign, and here we have a. So now the right hand derivative is given by a limit h tends to 0. We have f of 1 over 3 plus h because a is 1 over 3. Then we have f of 1 over 3, right? And here we have h. So now we have limit h tends to 0, f of 1 over 3 plus h can be obtained by replacing x by 1 over 3 plus h. So we have greatest integer of 1 over 3 plus h plus 3, and we have here f of 1 over 3 is equal to 3, and here we have h. So now we have limit h tends to 0, and this is greatest integer of 10 over 3. 1 over 3 plus 3 is 10 over 3 plus h, and here we have minus 3 over h. And we have just seen that the greatest integer of 10 over 3 plus h is equal to 3, right? So while proving the continuity of this function at x is equal to 1 over 3, we see that greatest integer of 10 over 3 plus h is equal to 3. So we have limit h tends to 0, and here we have 3 minus 3 over h. So this is limit h tends to 0. 3 minus 3 is 0 over h. So that is equal to 0, right? So the right hand derivative of this function at x is equal to 1 over 3 is given by 0. So now let us calculate the left hand derivative. So the left hand derivative is given by this limit h tends to 0. We have f of a minus h minus f of a divided by a minus h, right? So this limit gives us the left hand derivative, and the notation may also be used. This notation, that is f prime, here we have a and here we put a negative sign, right? So now we have limit h tends to 0, and f of a minus h is f of 1 over 3 minus h minus f of 3 divided by minus h. So this is limit h tends to 0. F of 1 over 3 minus h can be obtained by replacing x by 1 over 3 minus h. So we have greatest integer of 1 over 3 minus h plus 3, and here f of 3 is equal to 3 divided by minus h. So we have limit h tends to 0, and this is greatest integer of 10 over 3. 1 over 3 plus 3 is 10 over 3 minus h. Here we have 3 and divided by minus h, right? So we have seen that the value of greatest integer of 10 over 3 minus h is equal to 3, right? So while proving the continuity, we have seen that the greatest integer of 10 over 3 minus h is equal to 3. So now we can write limit h tends to 0, and this is 3. So we have 3 minus 3 over minus h. So this is limit h tends to 0. 3 minus 3 is 0 over minus h, that is equal to 0, right? So we can see that the left hand derivative of this function at x is equal to 1 over 3 is equal to 0. So viewers, we have seen that the right hand derivative is equal to 0, and the left hand derivative is also equal to 0 at this point 1 over 3, and we can see that the right hand derivative is equal to left hand derivative is equal to 0. So we can now see that, or we can claim that this function is differentiable at x is equal to 1 over 3, because the right hand derivative, it exists and it is finite and equal to 0, and similarly the left hand derivative, it also exists and finite and equal to 0. So right hand derivative is equal to left hand derivative, and both are equal to 0, right? We can also write the notation, that is f prime, and here we write a positive sign. Then we have 1 over 3 is equal to 0, that is equal to f prime. Here we write a negative sign, and here we have 1 over 3. So this is right hand derivative, this is left hand derivative, and both are equal to 0. So the function is differentiable at x is equal to 1 over 3. So from this discussion, we arrive at the result that the greatest integer function, that is x plus 3, is continuous and differentiable at x is equal to 1 over 3. Hello viewers, in today's session we are going to discuss one important and conceptual problem from differentiability of functions. And in this class we are going to discuss this problem in which we have to discuss the differentiability of this mod function, that is f of x is equal to mod of x plus 3 at this point, that is x is equal to minus 4, right? Now see, the modulus function is a continuous function for all real numbers, but it is not a differentiable function, right? Suppose we have a modulus function of this type, say f of x is equal to mod of x plus a, right? Now this mod function is continuous for all values of x, but this function, this mod function is not differentiable at this point, that is x plus a is equal to 0, that is x is equal to minus a, right? So for this point x is equal to minus a, this function is not differentiable, but it is continuous at this point x is equal to minus a. Now if we have the function of this type, say mod of x minus a, then this function is continuous for all values of x for real numbers, and this function is not differentiable at this point, that is x minus a is equal to 0, that is x is equal to a, right? So in our in this problem we have the function mod of x plus 3. So this function is continuous for all values of real numbers, but this is not a differentiable function at this point, that is x plus 3 is equal to 0, that is x is equal to minus 3. So this is the only point where this function f of x is not differentiable, and it is differentiable for other points, right? So here we are taking this point, that is x is equal to minus 4. So this function is going to be differentiable at this point, x is equal to minus 4. But here we'll see how we can prove that this function f of x, that is mod of x plus 3, is a differentiable function at this point. So the derivative of this function, it exists at x is equal to minus 4, but at x is equal to minus 3, this function is not differentiable. So with the help of the concept of left hand derivative and right hand derivative, we'll prove that this function is differentiable at x is equal to minus 4. So by the definition of differentiability of functions, we know that if the derivative of a function is to exist at some given point, then the left hand derivative must exist and it must be finite. And similarly, the right hand derivative must exist and it must be finite. And both the derivatives must be equal to each other, right? So if we have a point, say x is equal to a, then the left hand derivative at this point must be equal to the right hand derivative at this point, x is equal to a. So in this case, first we'll find out the right hand derivative, and we'll find out the left hand derivative, and we'll see that both the derivatives are equal to each other. So now let us first find the right hand derivative. So the right hand derivative is given by this notation, that is f prime of a, and here we write a positive sign, and we write limit h tends to 0 f of a plus h minus f of a divided by h. Now here a is minus 4, so we can now write limit h tends to 0 f of 4 minus 4. Here a is minus 4, so minus 4 plus h minus f of minus 4 divided by h. So now the value of f of minus 4 plus h can be obtained by replacing x by minus 4 plus h. So we have mod of minus 4 plus h over here, plus 3, then we have f of minus 4, that is mod of minus 4 plus 3, and here we have h, right? So now this is limit h tends to 0, and 3 minus 4 is minus 1 plus h, then here we have mod of minus 1, here we have h, right? So now we can rewrite this expression as limit h tends to 0 mod of h minus 1, and mod of minus 1 is plus 1, so we have simply 1 here, and here we have h. So now here we have mod of h minus 1, right? Now from the definition of mod function, see a mod of p is given by positive p whenever p is greater than 0, and mod of p is 0 when p is 0, and mod of p is negative p when p is less than 0, right? Now see here we have h minus 1. So if we take p is equal to h minus 1, then h is infinitesimally very small, as compared to 1. So h minus 1 is less than 0. So this is a negative quantity. So here a mod of p is equal to negative p will apply this property of or this part of this definition. So mod of p is minus p when p is less than 0. P is h minus 1. H minus 1 is less than 0. H minus 1 is a negative quantity, right? So a mod of h minus 1 is equal to negative of h minus 1. That is 1 minus h. So here we have limit h tends to 0, and here we have 1 minus h minus 1 over h. Now this one and this one get cancelled. We are left with limit h tends to 0 minus h over h. So this is the limit h tends to 0, and h get cancelled. We are left with minus 1. So this is minus 1 because this is independent of h. So limit h tends to 0 minus 1 is minus 1. So the right hand derivative of this function at this point is equal to minus 4 is minus 1. So now we can write here f prime of minus 4. Here we write a positive sign. So the right hand derivative is equal to minus 1. So now let us find out the left hand derivative. So the left hand derivative is given by f prime of a. Here we put a negative sign, and this is given by this limit h tends to 0 f of a minus h minus f of a divided by minus h, right? So this is limit h tends to 0 f of a can be replaced by minus 4. This is minus h minus f of minus 4 divided by minus h, right? Okay, so now let us find out the value of f of minus 4 minus h, which can be obtained by replacing x by minus 4 minus h. So we have mod of minus 4 minus h plus 3. Then here we have f of minus 4, that is the mod of minus 4 plus 3. And here we have minus h. So this is limit h tends to 0, and this is 3 minus 4 is minus 1. This is minus h, and here we have mod of minus 1, and this is minus h. So now here we have a mod of minus 1 minus h, right? So again we'll make use of this definition of mod function. So minus 1 minus h is again less than 0, right? Because here we have negative sign, here also we have negative sign, and h is a positive quantity, right? H is infinitesimally very small, but it is greater than 0. So minus 1 minus h is less than 0, that is this quantity is negative. So again mod of p is equal to negative p when p is less than 0. So mod of minus 1 minus h is equal to negative of minus 1 minus h. So this is 1 plus h. So minus minus plus minus minus plus, right? So mod of minus 1 is equal to 1. So now this limit is limit h tends to 0, and we have 1 plus h minus 1 over minus h. So now here we have limit h tends to 0, 1 and minus 1 get cancelled. We have h over minus h, and h get cancelled. So we have limit h tends to 0 minus 1, that is minus 1. So the left hand derivative of this function at this point, that is f prime of minus 4, here we write a negative sign, and this is equal to minus 1, right? So we see that the left hand derivative and the right hand derivative both exist, and they are finite at this point x is equal to minus 4, and both are equal to each other. So we can write left hand derivative is equal to right hand derivative. Hence the derivative of this function, that is f prime of minus 4, it exists. It means this function is differentiable at this point. X is equal to a, that is x is equal to minus 4, and f prime of minus 4 is given by the common value, that is the left hand derivative is minus 1, the right hand derivative is minus 1. So here we have minus 1. So we can say that this mod function mod of x plus 3 is differentiable at x is equal to minus 4.